So we're going to talk about what are called roots of real numbers. What do you know roots as when you hear the word roots? Like a square root or a cube root or a third root? God bless you. Not like a root of an equation.
Like something with something times itself is.
Yeah. You think of multiplication pretty much, right? You think of powers, you think of your exponents, you think of like, all right, 2 squared, 3 to the 4th, all those kinds of things involve roots or powers. So that's what we're talking about here in this chapter. We're finding the roots of real numbers, then determining what are called correlations that exist. Correlations are like trends. So the square root was invented to solve this equation. When x squared is equal to b, what is the answer? And we know that the answer is either radical b or negative radical b. Meaning it's plus or minus radical b. So if it was x squared equals 25, your answers are either 5 or negative 5. Okay, so we understand this idea, and I think a lot of you have seen this already in your previous algebra courses. We specifically call radical b the principal square root. Maybe jot that term down. Principal square root. Or simply put, principal root. And what that means, actually, let me give you a quick example, is that when you're asked to evaluate a square root, you're only really asked to find the principal root. But when you solve an equation, you find both of the roots. So let me show you what I mean. Here's the difference. If you have this, where it's an equation solution, a minute ago you all told me it's plus or minus 5, and I agree, right? Because x is really the square root of 25, and it's really plus or minus. Now, that is different from what's called evaluation. If I simply say to you, what's the square root of 25? You're literally evaluating it. The answer is simply 5. If I said to you, what's the negative square root of 25? It's negative 5. So when you solve an equation, you get both of the roots, the positive and the negative, because the equation has an exponent of 2. You need to get 2 solutions. If you're evaluating, and this is going to come up, that's why I'm doing this, based on like checking, in these problems you're going to plug the number back in to check that your answer is right. And when you evaluate, if it simply says square root of 25, you put 5. You don't put plus or minus 5, because you have to evaluate and come up with a number, a physical single number. Okay, it's the principal square root when you evaluate the square root of a number. Can this be possible? Could b be negative? When you multiply 2 numbers that are the same, can you ever get a negative answer? 2 real numbers? No. I mean, try it, 2 times 2 is 4. Negative 2 times negative 2 is also 4. The only way to get negative 4 is by using 2 and negative 2, but those aren't the same numbers, right? So this equation has no real solution. So when b, you can jot this down if you want, when b is less than 0, there is no real solution. And I'm underlining the word real because soon we're going to talk about, well, what if we can solve this with another number that we're going to make up? We're going to introduce some other number, and that's where you're going to see later something called the imaginary number system. Okay, but there's no real solution to this equation. All right, let's go with some examples. These are very simple. These are just evaluate, right? Evaluate. First one. Call it out, obviously. 2. Second one? Negative 4. Third one? 3/5. If you were confused about the third one, just look at it. It should make sense if you pick up. Just look at what happens, right? Root 9 over root 25 is just simply root 9 25ths. So just make it root 9 as 3 and root 25 as 5, or simply 3/5. The middle one is negative y. Why is the middle one negative?
Because there's a negative sign.
Exactly, because there's a negative sign. Not because we're looking at positive and negative answers, because we are evaluating, and when we evaluate, we only look at the principal root. We only look at the principal root. Now, for example 2, though, same process now. And I'm stupid. I shouldn't use 25, but whatever. Same thing earlier. The answer for the first part, positive or negative 5. The second one, part B.
Positive or negative 7.
Positive or negative 7? Now, if the 49 were on the other side, that would probably work. Try plug 7 in.
Or it wouldn't make any answer because there's no square root. Negative 49.
So what would your answer be given as then?
No solution.
Good. No real solution, actually, because you got to move it over, right? So before you take the square root, you got to isolate x squared. Because in part B, x squared is being added to 49, you can't actually square root it yet. You got to move the 49 over. And then as a result, we try to say, well, it's just the square root of negative 49. But right now, we don't know how that works. So we say no real solution. Part C? There's 2 ways to do part C. George, give me one way. All right, so move 20 over. And then divide by 4. So what's the answer, George? Give me the exact answer. Yeah.
3, 6.
No, I want the exact answer.
Square root of 5.
Thank you. Ah, you like that. See, a lot of students, when you hear exact answer, they try to give you like 40 decimals. You can give me as many decimals as you want. Is that ever exact? Because radicals are irrational. So those decimals go on forever with no pattern. So if you ever try to give decimals and round something, it is not exact. The exact answer is plus or minus radical 5. Okay, and that's how I would leave that as an answer. I would not put a decimal estimation. You should know your numbers though, right? What's the square root of 4? 2. What's the square root of 9? 3. So this answer is between 2 and 3. Does everybody pick up on that with square roots? How to estimate square roots? What's the square root of 37? Probably.
6.
It's a little bit more than 6, right? How much more? Well, you don't really know. In calculus, you'll learn how to do that by hand, actually. It's kind of cool. You can get all all square roots of any number by hand without ever using the calculator. Interesting to think about, right? Try and do that without calculus. Like trying to find out the square root of 39. You could sit there and try numbers, but without a calculator, that's annoying to multiply 6.1 times 6.1. It doesn't work. 6.2 times 6.2. So there's techniques that you're gonna see. Now that's one way to solve this, right? Another way to solve this, actually, anybody see another way to solve this? It's not obvious, that's why. What can I factor out? I'll give you a little hint.
Oh, we can factor out 4.
Yeah, take out a 4, leave them behind. Right? Now what happens to the 4, really? Does it have any effect on this? How do I factor x squared minus 5? What does that factor into?
I was thinking that you just do a thing where like take 4 does not equal 0, and then x squared minus 5 equals 0, and just
Yeah, and this would give us the same answer as before.
Yeah.
Exactly. So there's 3 ways to do it. That's the second way to do it. This is clearly not true, so this doesn't help us. But if I didn't want to do it that way, and I factored out the 4 instead, and I got to here, this is what's weird. See, you don't see it because it's not obvious, but it works. Come on. There's a difference, right? You see a difference in there? X is squared. 5 is a perfect square, isn't it? What is 5 a perfect square of? I'm kind of stretching the word perfect there. It's really not perfect.
2.2360.
But what is the exact value of the perfect square of 5? What is it?
Just the square root.
The square root of 5. So technically speaking, ready for this? This is what gets kind of weird. I can think of this as difference of squares and put plus or minus radical 5. Yeah, think. Luke, if this number were 4, what would you put here and here, Luke?
2 and 2. And
Because what's the square root of 4?
2.
Well, what's the square root of 5? Do you know? No. So you put root 5 and negative root 5. And then what would your answers become as a result?
Plus or minus.
Yeah.
Is it possible to have square roots of square roots?
Sure. Absolutely. It's the square root of the square root of 9. It's the square root of 3. You know what I mean? You can have as many square roots instead of as many square roots as many as you want. You would write a radical, and inside the radical would be another radical, and then the number underneath it. Yeah? But I'm trying to show you guys different ways of viewing things. So we've learned difference of squares all year, right? And we always learn it as x squared minus 9, x squared minus 4, x squared minus 16. That's always the way we look at difference of squares. But really, x squared minus anything is difference of squares. How do I factor x squared minus 3? Factor x squared minus 3. What would that become? Come on, this is easy. X squared. We just did x squared minus 5. You have it in front of you.
X is minus, or plus or minus.
X plus root 3, x minus root 3. That's what x squared minus 3 would factor into. Do you see what I'm saying? Everything can be factored with difference of squares if you have a difference anywhere. If I had this, let me add a slide. If I had this, 19 minus y to the third. Technically speaking, those don't look like perfect squares, do they? But I could factor this into root 19 plus root y cubed times root 19 minus root y cubed. Because technically the rule of difference of squares is to say take the square root of this, put it here, take the square root of this, put it here, and then put plus and minus. Well, that's what I did. So that is actually the correct factorization of that. Although would you really do that? Probably not, right? It's probably not something you're going to have to actually do. But I want to show you this because later in calculus, you're going to factor things that end up with binomial conjugates. And we'll talk about those in like maybe a lesson or two, where you have answers of 2 plus root 3 and 2 minus root 3 as your answer. Is that clear? Okay, so you're going to have to do stuff where you're going to get answers that involve radicals in the answers. So I'm just trying to show you a different viewpoint on difference of squares. Because this is difference of squares, whether you want to agree or not, it is. Okay, and if you don't believe me, remember always go back to your rule. Pick a number like this, and this will become 2 and minus 2. Well, where did they come from? You took the square root of x squared to give you x. You took the square root of 4 to give you 2. Do the exact same thing here below. Does this ever work with a sum? No. Okay, if there's a sum, it doesn't work this way. If there's a sum, we'll talk about those other types of numbers, and those other types of numbers we're going to see are those non-real numbers that I keep alluding to. How about a cube root? It's up here what it says, but somebody else explain what is a cube root exactly? How's that different from a square root? Lou?
It's like instead of finding the number that times itself twice, you're finding a number that times itself 3 times.
For example?
Like the cube root of 27 is 3.
Why?
Because 3 times 3 times 3 is 27.
Good. Did everybody hear that? Is it loud enough? Okay, the cube root of 27 is 3 because 3 times 3 times 3 is indeed 27. So a cube root is very similar to a square root, but here we're looking for a number that repeats itself 3 times. Yes? All right. Some examples. We have, Luke gave us part A already. His example was root 27, or cube root 27 is 3. If you take 10 squared times 10 squared times 10 squared, you don't have to check with your calculator. You don't even have to know what this is. All you know is your rules of exponents. What do you have to do to these exponents? You have to add them. 2 plus 2 plus 2 is 6. Thank you. 2 plus 2 plus 2 is 6. So can somebody, actually let's go to part D first. So this is just 10 squared as an answer. Part D, what would that one be? The cube root of d to the 12th. The cube root of d to the 12th. D to the 4th. Because again, isn't this true? So therefore your answer is simply d to the 4th. Hey, so please do me a favor. Use part D to generalize a rule that you could come up with. Look at example D and come up with a general rule that'll make this easier for me. George?
You can divide the exponent inside
By the? What was the other word? Did I use this word yet? I might not have used this word yet. Oh no.
the radicand.
It's not. The radicand is d to the 12th. 12 itself is the exponent. D itself is the base. What is that 3 on the outside called? I'm going to go over it in a second. It's on the next slide. You can look ahead. I didn't realize I put it on the next slide. Go ahead. Index. So your general rule here could be the following. Take the exponent and divide it by the index. Now, if the index cannot divide evenly into the exponent, though, we're going to run into some problems, and we'll see how to do those later. Okay, but for now, we'll make it work so that happens. So 12 divided by 3 is indeed 4. All right, so here's our terminology. We need to know the terminology. Listen, please listen. You guys are so interested. It's good that you're doing that. I'm saying just listen for a second of what you're doing. So the terminology we need to know. N is the index. You got to know that word. It's the index. The radicand is whatever's underneath the radical. That symbol is called the radical. This underneath is called the radicand. That's the B value. And N is the index. So generally speaking, we could have what's called the nth root So if n is 5, now I'm looking for a fifth root. Or if n is 6, I'm looking for a sixth root. But pretty much n is the number of times that object or number has to multiply itself. Okay, n is the number of times that it has to do this. Hey, what's the index for a square root? It's nothing there, but what is it? Thank you. It's 2. Does everybody see that now?
Yeah.
Because if it's a cube root, we're looking for a number multiplied 3 times. Fourth root, that number has to multiply 4 times. So a square root really has a 2 outside, but it's not written. But there really is an index of a 2 for a square root. Just like x is really x to the first power, but you don't write it that way.
Radical is just an include symbol, right?
Correct.
And that's how it's referred to.
Correct. And you can even speak it that way. You could say radical 7 plus radical 8. But if I had a cube root, I'd say cube root 7 plus cube root 8. Instead of saying square root 7, square root 8, radical is easier to say. So you can use that as a terminology. So let's look at these next few here. Can you come up with a number that when it's multiplied by itself 4 times gives you negative 16? That's the first question, really. That's how I have to translate that in my head. Pick a number, right, that when multiplied by itself 4 times, why 4? Why 4 times? The what? Index. The index is 4. So the index tells me I need a number multiplied 4 times to give me negative 16. What number is it? What do you got? What do you got? What do you got? You're shaking your head? You're saying? Yeah. What did you start with originally? Yeah. Yeah, because negative 2 worked for 8, didn't it? Yeah. And you think, oh, negative 2 because negative 16, that makes sense. But when you think about it, negative 2 times negative 2 is positive, times negative 2 is negative, times negative 2 is back to positive. So there's no real answer for this, right? Let's jot that down. Recording, really? If something is greater than 0, it means that it is positive, right? So the radicand has to be greater than 0 for it to be a real solution. You need a real number to be expressed by that. So we set the radicand, if you want to jot this down, you can, set the radicand greater than 0. Now, in these cases, 0 works too, doesn't it? What's the square root of 0, everybody?
0.
So I can put greater than or equal to really here. So let's add that little equal to symbol beneath the greater than. Because it could technically be 0 also. It could be 0. Solve for x. George, x is? Greater than or? Very good. Give me a number less than 3. Pick a number less than 3. 2. What's 2 minus 3? So you would get the square root of negative 1. That wouldn't work. Oh, there it is. Okay, so your answer is everything greater than or equal to 3. Everything greater than or equal to 3. How about the second part? Same approach, please. Same approach. Set the radicand greater than 0. So let's start with that. That radicand is a little bit more tricky, but let's set it greater than 0. Greater than or equal to 0. Who remembers their notes from 4.9? Who remembers how to do this? Section 4.9. We got a quadratic inequality, right? It's quadratic, it's an inequality. What do you have to start by doing?
Well, you actually treat it as if it's equal.
Good.
And then you solve as if you normally would. And then those points that you get are your the really important ones.
Good. The word critical, but it doesn't matter. Really important works too. That's it. And then what do you do with those points?
You put them on a number line and then you test positive or negative and whatever works with the inequality sign.
Perfect. Okay, so we got to remember that this is a quadratic inequality, and that's exactly the approach we would take. Factors become x what and x what?
Minus 7 plus 3.
Minus 7 plus
3. Or
4.
3.
I have 4.
Oh,
4.
plus 4, sorry.
Because the 3 is in the middle. Right? The middle term is 3. That's what you're saying. So my answers are 7 and negative 4. And those are my critical points. I know it's a closed circle because it's greater than or equal to. I happen to remember by now that greater than or equal to is a disjunction. I'm going to shade that way. I just remember that. When it's less than or equal to 0, it's going to be the middle region. How do I know that? Remember the shape of this graph? What does the shape of a parabola look like? Does it look like this?
Yes.
When is it going to be above? Here's the x-axis. When is it going to be above the x-axis? When it's outside of these regions, right? So we're going to end up shading this way. I can tell you already. When is it below the x-axis? When is this parabola below the x-axis? Between where? Between the 7 or the -4 and the 7. It would be below the x-axis right here. So we visualized this, if you guys recall. We drew a graph of this earlier in the year. So it would be at -4 would be one x-intercept, and 7 would be the other. And this quadratic would definitely look like this. The y-intercept would actually be down here at -28. Okay, in case you're wondering, where does the y-intercept come from? Take a look right here at your constant. And we'll go over that really later in chapter 7. We'll do a lot with quadratics, a lot more than just this. So if we look at this function, we can clearly see this is saying, when is, ready? I want you to see this and translate, please. When is the quadratic itself greater than 0? Or when is the function above the x-axis? I need you to understand that those mean the same thing. Okay, so you have to look. When is the quadratic greater than 0 means when is the parabola or the function itself above the x-axis? Well, it's above the x-axis out here, and it's going to continue in that direction forever. So think of this as my number line right here. I'm going to shade everything out that way and out that way, which is meaning shading here and here. I can obviously test points, which we've done in the past, which is what I encourage you to do. If you test 0, plug a 0 in the middle region. 0 here and 0 here makes this negative times a positive, right? Plug in 0 in both spots. Negative times positive, which is negative. So the middle region is negative if I test, and these are positive. These signs are indicative of where the function is. Below the x-axis mean the y values are negative. Above the x-axis mean the y values are positive. Tristan, go.
Yeah, we just tell that by x squared being positive or negative too. Right? If x, like the parabola itself, x squared is negative, it's probably going up.
Yeah, so if it was negative x squared,
Yeah,
if it started with negative x
then
squared,
it would be in the middle,
the
right?
parabola would be going down like that.
So the center area would be.
So the center would be above the x-axis. But if I switch this sign to less than, you need to then re-represent that in your mind. Less than or equal to 0. In those cases, from 4-9, we did those other kinds. In this case, it's always going to be greater than because it's the radicand. But if this were less than, we have to look for what's below the x-axis. Okay, but I want you to see the analytic and graphical approach to the same problem. Right? This is the analytic example or the analytic solution where you apply values and test the regions to see which is greater than 0. Well, positives are. But the graphical way to look at it is saying which is above the x-axis. That's what greater than 0 means. Which one or which part of the graph of this graph has y-coordinates that are greater than 0. Here and here, the y-coordinates are greater than 0. In this region, the y-coordinates are negative. So our answer for this last part is going to be a disjunction, x less than or equal to -4, or x greater than or equal to 7. Homework for tomorrow, you know. Okay, standard homework. Make sure to get through it.